Students, this is starting our rotational kinematics. And this is the thing is we use some Greek in some of this already. When we talk about angles, we've used theta and occasionally we used phi and maybe once or twice we used alpha and beta. And those are just angles. All right, that's what we intended at that time. But now when we start talking about essentially what we're talking about is now we have a circle something's moving on, right? And let's say that we want to talk about motion where this object starts here and it ends up somewhere up there like that. And so instead of talking about, which what I'll do in green, instead of talking about this distance, which here would be delta x or s, I'll call it s for now. We're going to instead talk about this angle. All right, so in your math classes, you may have talked about, in your trig, talking about this angle. This is what we're going to call theta. All right, so this is going to be theta. And there's a relationship between s and theta here. In your math classes, it's very simply s is r theta. That's all it is here. The arc length S is R times the angle. So this theta is the angular displacement. Now, after we define that, everything else comes from doing the same sort of stuff here. Is our velocity v is ds dt or dx dt. All right, we use delta x or we use s kind of interchangeably. So for angular velocity, we're going to use the letter omega, which looks like a W, but it's a lowercase Greek omega symbol. And this is going to be omega is d theta dt. So what that means is this motion happens, right? We have this movement from here to here. Well, we can also write the rate at which that happens. ds dt is your tangential velocity, which is this thing is trying to move at some angle like that. Sorry, at some tangential velocity that way. All right, what's happening is it's going around a circle. So we have this, and we can relate it to the angular variables, d by dt of r theta, just plugging in what s is our tangential velocity. And I'm getting alerts about what meetings I have to do tomorrow. That's fun. So R never changes. This is something moving in a circle. If we have a thing rotating, right, like say I have this piece of tape and I mark a line on it there. If that rotates, it rotates around the center of this thing, the radius never changes. So that radius is constant, and what we should get is r d theta dt. And so we'll get an expression here that this tangential velocity is r omega. Now, we can do the same thing for the acceleration. It's going to be dv dt. Well, we can take a derivative of this thing as well. So over here, the thing that we're calling angular acceleration is going to be alpha, right? And it will be alpha is the rate of change of your angular velocity with respect to time, d omega dt. So if we look at this, then our acceleration should be the rate of change of our tangential velocity, which is d by dt of r omega. But again, r comes out of the derivative because it's a constant. And what we'll have here is our angular acceleration is r times alpha. So what this does is it gives us a few different definitions here. We want to keep this because that's just defining how something moves in a circle. We have the definition of velocity and the definition of acceleration. And we have ways of relating the translational variables to the angular variables. All right, what we have is the tangential velocity looks like r omega, and the acceleration looks like r alpha. So these 5 things are kind of important. We also have, if you remember, we have kinematic equations. And I'll write them out, and I'll use S instead of delta S. So S was Vt plus 1/2 At squared. We had S is 1/2 V initial plus V final T. So there's a V initial here. We had V final is V initial plus AT. And we had V final squared is V initial squared plus 2A. In this case, I'll use S instead of delta X. So those were our 4 kinematic equations. Well, we have, by just substituting in, S is R theta, and V is R omega, and A is R alpha. Right, substituting in for angular variables, what we'll notice is that every term gains an R and they just cancel out. And this is perfectly fine. What's happening is we defined relationships between S and V and A, between the displacement, velocity, and acceleration. They're just, each one is the derivative of the previous one. And that's true also for the angular variables. We define theta, and then the angular velocity is the derivative of the angle with respect to time, and the angular acceleration is the derivative of angular velocity. They're the same relationships. So all this is a variable change. So we're going to have kinematic equations here. We're going to have theta is omega initial t plus 1/2 alpha t squared. We're going to have theta is 1/2 omega initial plus omega final t. We're going to have omega final is omega initial plus alpha t, and omega final squared is omega initial squared plus 2 alpha theta. So we're going to have the same relationships, but now instead of talking about motion that is translational, which means it's moving up and down, right and left, in and out of the page, we're now going to talk about stuff that is moving. Some point is moving in a circle. And so we'll have kinematic equations here in red, and we'll have these definitional equations. So what I'm going to do is write all of this out one more time so that you have it, so you can have it in front of you. All right. So we define our angular distance or angular displacement. S is r theta. Then we define velocity, so displacement, and then velocity, and then acceleration. Here we define our angular velocity as change in angle with respect to time, and we define our angular acceleration as change in velocity with respect to time. And that gives us, based on this and the definitions of regular velocity and acceleration, that gives us tangential velocity is r omega, and the tangential acceleration is r alpha. And we have one more equation. This is something that's moving in a circle. So we can use, at any given instant, we can use that it's moving on in a uniform circular motion. So we can use that this is our tangential acceleration, but our centripetal acceleration is v squared over r, which is r omega squared. So we'll have an extra equation. And then we have our kinematic variables. So our kinematic equations. We'll have theta is angular velocity times time plus 1/2 angular acceleration times time squared. We'll have theta is the average angular velocity, which is 1/2 final plus initial times time. We'll have our final angular velocity equals our initial angular velocity plus acceleration times time. And we'll have the angular final velocity squared is the initial angular velocity squared plus twice the acceleration times the time. Times the angle. So one thing some of my students do, that looks like a fish. They call it fish for some reason. I don't know why. It's alpha. Right? So so we just have theta and omega and alpha. So for the rest of these problems, I'm going to try to use theta to mean a displacement. And any other time I need an angle for some reason, I'll use something else that's not a Greek letter in here. So this is a definitional video, and it went 12 minutes here. And I will do problems with this. This is not a, we're going to just leave it there. We're going to practice this. But you've done this before. The context is different, right? The physics is different. Instead of something moving in a straight line or in a parabola or even in a uniform circle where it's an object orbiting something, now it's an object rotating. So the context is different, but the underlying math is exactly the same. And so we're going to use this stuff exactly the same way. So the next couple of videos, we'll do some practice problems that hopefully make sense in regards to the homework. And we're going to talk about a couple of other things along the way. We don't have, like these things are vectors. I haven't stated anything about the vector quantities yet. I've just stated stuff about the numbers. But these things are vectors, and we when we talk about motion around the circle, we can define S in a sense. We can define the tangential velocity, and we can define some idea of the acceleration, which will have a centripetal part that's into the circle and a tangential part that's tangent to the circle. But what does it mean for any of the angular variables to be vectors? And it's going to be kind of a weird thing. So that's going to be the next video. Anyway, here it is. So you can have it at the end of the video. You can look this stuff up if you would like. Be careful. Things are alpha, not 2. I'll try to do that better. Maybe that's better. All right. But you're going to do problems exactly the same way here.